So yes, once again, welcome. Thank you for joining us here today. Our presentation, the webinar, looking at an interesting application, but measuring the thermal, and also we're going to take a look at the mechanical properties of condoms. This is an area of research which, although, might seem off to the side in some cases, there's application here on, method selection for things like thin films, which we'll talk about, where thermal conductivity and the mechanical properties play a significant role in both the manufacturing process, production, QA, QC. And yeah, that's what we'll be really diving into. It's an interesting application, but I'll just say right at the start here, over the past, I think, maybe 6 or so months, there's been quite a few inquiries from groups actually looking to quantify performance of these condom materials, some from researchers, others more on industry. But if thermal conductivity plays a role, there's certainly an application that we'll take a look at, and that's what we're doing here today. So my name is Ari Hakimian. I'm an application scientist here at C-Therm Technologies, and I will be joined a little bit later in today's session by my colleague Arya Shadowstambik, who will be talking more on the mechanical side of the material characterization. So going into it here today, just a little bit of an intro for those that may be new to C-Therm. Want to let you know really who we are, what we do. So at our core, we are experts in thermal conductivity. Specifically the transient class of measurement technique. This will be, of course, the main focus for the thermal conductivity assessment side of things in today's session. The instrument that is featured in the data collection, and again, our core product here, Trident. Trident was developed as a modular platform, providing different methods for thermal conductivity testing. Really, when, the idea behind Trident here with the modularity and the different options are to provide just that, different tools to address your specific task at hand. Sometimes this is related to the type of sample you're looking to test, the size that you have available to work with, or the testing conditions of interest. Being able to pick and choose the best option is really going to give you your ultimate chance for the best success on the data collected. And this quote here, it's one we like to use, and it really embodies, the idea behind Trident. When all you have is a hammer, everything looks like a nail. So really this stems from the fact of, if you're really locked in with just one way of doing things, you're going to try to make everything fit into that bucket. And a lot of times, really good methods that, for example, might do really good at testing a solid material aren't great at doing, let's say, a liquid. So again, really being able to pivot into a method that is best suited for that sample or that testing profile is going to ultimately give you your best possible data output. So for those that may be new to thermal conductivity, this method selection guide is a nice resource. It's available as a free download on our website. And my colleague Angad, who's monitoring today's session, he's going to be posting some links into the chat throughout. So definitely feel free to take a look at those. But this guide just gives a nice overview of different thermal conductivity methods that are available in industry. Also, of course, the transient options that we have here on the Trident platform. A nice way to kind of dip your toes in and get some understanding of where these different tools can be employed in your characterization projects. I'll also just put a little plug in for our partners. So we are partnered with Rigaku for their line of thermal analysis tools in North America. So DSC, STA, and TMA instruments, as well as Metrovib, Metrovib's line of DMA for mechanical characterization. So in today's session, we'll be focusing primarily on, of course, the Trident thermal conductivity and some Metrovib characterization from the mechanical side as well. Lastly, Thermal Analysis Labs is C-Therm's contract testing division. Folks who may be interested in getting some data, but maybe you're not ready to bring the instrument purchase in-house at this point. Maybe you just have a lower volume of samples, but you still need to get them tested. Certainly feel free to reach out. All the options that we have available through our, for capital equipment purchase, they're also available as testing services, as well as other methods that are in industry that might be of relevant interest to you. So in either case, definitely happy to support different projects, whether that's from an instrument acquisition standpoint or through contract testing services. And before we jump into the bulk of the session here, just wanted to end with a client testimonial. We always try to pick one from the website and share it. We, of course, love to hear what our clients have to say about us. This one is from Sebastian at BChem, kind of noting the C-Therm solution provides quick measurements, requires only small sample amounts, and accurately and consistently measures high thermal conductivity materials. The software is clean and intuitive. C-Therm support has been top-notch at all times. So always nice to hear the positive things folks have to say. We do have a list of testimonials available on our website if you did want to check out what folks are saying about their experience with us. Okay, so this brings us really to the start of the main presentation here. So, from my side, I thought I would, as I'm like looking into this application in this area, it's certainly an interesting topic. We all know what a condom is, but maybe some of the background on where they came from and really where they've progressed to today's times could maybe be quite insightful. I mean, with any product or any technology, of course, they've evolved over time. So I want to do a quick brief history on condoms, where they started from and where we're at today. We'll get into the thermal stuff here shortly, but just want to add some context. As I was researching, there was some data to suggest that Les Combes Barrel is a famous cave in France. There were depictions of what some are suggesting are some of the earliest representations of a form of a condom being introduced as early as 12,000 to 10,000 BC. There is some debate on if it was actually, quote unquote, a condom in that sense, but that's really, I think, where the earliest form of documentation, I'll call it, was found. But really more toward into the early 1700s, there's a lot of collected samples that still exist on a variety of animal skin based protection. So here there's a sheepskin. I believe this was found it's in an Egyptian museum depicting what was, again, used at the time. Really kind of skipping ahead here to 1855. This is where the first form of rubber was used in the formation of condoms. This presented a pretty significant shift away from, animal-based products for this form of reproductive protection. And then most notably, and really where we stand today, latex was introduced in the 1920s, and this has been predominantly the main material used in the development of condoms that we know today. So latex condoms. Really, latex is the most common material used in condoms. It makes up about 80% of the total market share. There are non-latex versions, and we'll kind of do a quick comparison of performance between a latex and a non-latex material here coming up. But of course, there are also still some of the animal skin products that are used in a very smaller percentage, but they still exist here today. Now, in terms of latex manufacturing, looking at the process here, essentially involves this dipping process and within there is the combination of both thermal and chemical processing in order to go from that liquid latex state to the formed product. And looking into some of the processes here, a lot of the quality assurance testing that is done in production involves the mechanical side of things. So this will, dovetail nicely into what Ario will be speaking about in his section, where those mechanical properties are also quite relevant. Now, focusing here on the thermal side. So the role of thermal properties, it comes into a few different areas. As I mentioned, some of the processing, the performance of the material itself, user experience. A lot of this is inherently related to the thermal characteristics of the materials involved. And thermal conductivity being a key parameter here of interest for many groups. So thermal conductivity, of course, defines a material's ability to transfer, conduct heat energy through a body of material. Interestingly, to note that, again, depending on the application, sometimes a high thermal conductivity is desirable, and sometimes a more lower conductivity, more insulative is the goal. So high or low thermal conductivity being good or bad is quite subjective to the application in mind. One thing to note about latex is that, generally speaking, it is more on the lower end of the thermal conductivity range when we look at, all the materials that exist out there for that can be tested. So latex, depending on the specific formation, the considerations on the processing and the density, it's typically around 0.1, 0.2 watts per meter Kelvin. It can be lower or higher depending on how you're treating it, but it's generally on that lower side of the spectrum. And again, looking through some of the really what's available in out there in industry and products that exist, there's been some interesting work in next gen condoms introducing additives and fillers like graphene. We do a lot of work with groups in different industries where fillers are being introduced into materials. These are, of course, used to tailor specific performance criteria. For example, thermal interface materials, they're a polymer, but you're adding in quite a lot of conductive fillers in order to hit a certain threshold of performance. And interestingly enough, this is also happening in the condom space. So graphene introduced, kind of, see some of the marketing claims, 85% more body heat transfer through the sample, through the material. Kind of interesting to see that, as materials in general are advancing, we're seeing that in really any industry trying to adopt some of these similar ideas in how to further improve and enhance performance. Some interesting research I found here is actually on some work to develop an inherently new material for condom application. So hydrogels. Hydrogels aren't what I would say necessarily new. They've been around for quite a while, but Dr. Robert Gorkin, who's a researcher at a university in Australia, is actually pioneering some research on the development of hydrogel-based condoms. Which has some interesting applications. Hydrogels, there is a lot of work being done in industry, in industry and also in academia for using hydrogels as biomedical scaffolding materials. So you can actually impregnate the hydrogel with a specific drug, antibacterial, different for drug delivery in a variety of applications. But for use in condoms, where a lot of those, the lubricants or some of those medications are being, coated on the condom itself for improved, protection and health considerations. There's a potential here to actually just integrate that directly into the material of a hydrogel. So interestingly to see where some of the groups are focusing research on. And yeah, again, because like I mentioned, 1920s was really where latex began to be a predominant material used in condom manufacturing. Who's to say in a few years it might not shift to a new material with some other advantages to take into account. Now, I also wanted to touch on another thermal property, thermal effusivity. This is one that if you've been on our webinars, we talk about a lot in terms of the warm feel, cool touch of a sample. Thermal effusivity is sometimes referred to as thermal inertia. It defines a material's ability to exchange heat with another body that it's in contact with. Again, when we're talking about that perceived feel of something, any type of product that is going to be in contact with the human body, understanding the thermal performance can not only be, again, from just a general performance standpoint, but again, the user experience. A lot of work in the effusivity space revolves around textiles, fabrics. So, like the shirt that I'm wearing, is this, this thicker, warmer feeling material is being used in, of course, a lot of winter wear where you want to feel warmer or cozier, whereas, someone developing a product for the summer where you're trying to keep things cool, you might want to use something else to accommodate that, that level of comfort. There's been some work done in collaboration with C-Therm and a few different industry or academic researchers. This has been featured in some previous webinar content, but work with the University of Oregon, taking a look at really correlating the perception to of a human touch panel to the effective thermal effusivity of these materials, in trying to, again, quantify where do the effusivity values line up with the perceived feel of a human subject. So generally speaking here, higher thermal effusivity will correlate to a more cooler feeling material, whereas something lower in effusivity is more warmer feeling. But again, tailoring that specific, output can be important, because if you are inherently having something that is, too high in thermal effusivity, it's going to feel too cold on you. That may be beneficial in some areas of application, but, in terms of user comfort in others, it may be a negative. So looking at from a lens of thermal conductivity and effusivity can provide some nice framework for quantifying the overall picture and how those materials will behave. And of course, a condom is going to be in direct contact with the human body. So understanding that as a performance metric can also provide some different benefits to both, the R&D side of things, as well as, looking at, production and ensuring that it is meeting specific requirements of those groups. Now, coming back to the idea of the thin film, because inherently a condom is a very thin sample. So testing thin films is an area that is sometimes challenging due to the inherent size of the material, the thickness that you have available. Many techniques out there in industry, while again, very poised to test larger bulk materials, a variety of insulative or conductive samples, can sometimes be challenging with something like a thin film. When we look at really the options of how to best approach testing of something of that nature, micron range thickness, the TPS, or Transient Plane Source, really comes out as a front runner and one of the better options that exist. The TPS, which conforms to the ISO 22007-2 standard, there's some specific guidance on how to do thin films characterization. It's a specialized function within the Trident platform that we offer in testing samples of that size. If you've never really looked at how this happens, I'll give you kind of a very high-level rundown of the process involved in testing thin films with TPS. It's essentially a three-stage process. We have our TPS sensor, and we actually will always have a conductive backing material, which is placed on either side of that sensor for testing. The first measurement we actually always do is just with the backing. There's no thin film involved. This is to establish our, effectively our blank or our base point, our zero measurement for the system. The second measurement that we will take is then taking the same setup, but introducing one layer of a thin film on the top and bottom side, taking that measurement, and then we'll repeat this one final time with a second layer of the film. So essentially, for a test with a thin film, you will require 4 sample pieces cut to be placed in this type of setup for analysis. This is just a little screenshot of an example polymer thin film that was tested. You can kind of see what the data looks like. This is just a little snapshot from the Trident software. And you can see the general idea in the process here. Essentially, the bottom graph there, we are taking a measurement of the change in temperature as a function of film thickness, of material thickness. And by building out this correlation, assessing a good linear, quantified by a good linear structure within the sample, this is how we go about quantifying or validating the measurement. But essentially, it's a three-part test. Start with your control, one layer of film, two layers of film, and we're looking to assess the linearity between those points. This has been featured in previous content, but just some example of like, I would call them more standard thin film materials tested on our system. Again, whether it's something like a Kapton, Mylar, again, thermal conductivity does range depending, of course, on the material you're looking at. But again, generally in that 0.1 to 1 watt per meter Kelvin range is where most of the thin films that we see coming in at. All right, so this brings us to some of the actual application data that we collected on the condom samples. So in this study, we did a quick assessment looking at really the difference between a latex and a non-latex condom, trying to see, are they similar? Are they vastly different? And where do they fall? So we did this from both a thermal conductivity perspective using the TPS thin films setup for the conductivity measurement. And then from the effusivity side of things, this was done with the MTPS, or modified transient plane source. Really, the big difference in the setup here is that for the MTPS, due to the thickness requirement for the sample, we do need to stack up enough material to achieve, a few millimeters of thickness compared to the thin films option, which is, again, just taking a couple layers of the film for the testing. So on the far left there, you can see the TPS thin film setup. Again, quite simply, the TPS sensor with that conductive metal backing, which is a stainless steel, and then some of the condom that was placed on the top and bottom side. But from a results perspective, we can see that comparing the latex and the non-latex versions, there was a notable difference in both the thermal conductivity measurement tested on TPS and a very similar trend observed in the effusivity from the MTPS. So again, kind of showing that the non-latex version actually was higher in thermal conductivity than the latex counterpart. I will say some of this work is being developed also into more of a we call them application highlights, more of a write-up on the doc, gives a little document to describe a little bit of what was going on in the measurement, how it was set up, and so forth. That will likely be posted to our LinkedIn here in the coming days. Inga just posted something there. Maybe it's already posted. So if you did want to look at kind of a little bit more on the write-up and what was done there, definitely feel free to check that out. But this brings me to the end of the conductivity side of things. At this point, I'll invite, again, my colleague Arya to jump in and take us through some of the DMA.
Alrighty. Hello, everyone. Thank you so much for joining us, and thank you, Arya, for the thermal conductivity portion of the webinar. So as Arya mentioned, we're looking at applications and for condoms and different properties of the condom material. And we looked at two different types of condoms, one polyurethane-based and the other one latex-based condoms. I am going to talk about the dynamic mechanical properties of condoms here and the use of DMA instrument in applications related to condoms. So first, I'll be talking a little bit more about the DMA principle, but just to note it here, we did 2 other webinars for DMA. So if some terms are not familiar with you, you can easily go to the website and watch those webinars. And yeah, without any further ado, I guess I'll jump on DMA principles. So DMA is dynamic mechanical analysis, and that's the only and the most accurate technique for measuring viscoelastic properties of viscoelastic materials. And so the basics of DMA includes applying a dynamic force excitation to a specimen of material and measuring the applied force as a response to the deformation. A very important point about dynamic mechanical analysis is that it's unlike static tests where a constant load is applied in different forms like tension or compression. And DMA tests are dynamic and a periodic load is applied on the sample. As you can see, here's a simplified test setup for DMA instrument. And there's a piece of sample between two sample holder, between the clamps of sample holder, and it dynamically deformed the sample. And from that data, we can see we have, as a result, we have force and displacement. And there's a delay due to viscoelasticity of the material. There is a delay between the force or displacement applied and the response, which is called phase angle. And tan delta is related to that phase angle. And after this slide, I'll be talking more about the parameters that we can essentially obtain from a DMA test. So DMA, as I mentioned before, can deform your sample for the testing purposes. And this deformation can happen through a variety of deformation modes: tension, compression, shear deformation, and bending. For this application, for condoms, we use tension deformation since it's more related to the deformation happening to the material in its use. So from a DMA test, can obtain many parameters, but the main ones that we'll be looking at will be modulus, elastic modulus, and viscous modulus, and tan delta. So complex modulus, which you can see on the top, is basically the overall resistance of material to deformation. And it's basically the ratio of stress over strain. And this parameter, complex modulus, has two parts in it, which is the elastic or storage modulus part, and the other one is viscous or loss modulus. So starting from elastic modulus, basically elastic modulus or storage modulus expresses the ability of the material to store energy. And you can see the formula. And again, if you want to dive deeper into these terms, you can watch the other two webinars and application and theory of DMA. And the other component is the loss modulus, or the ability of the material to dissipate the energy through heat into the matrix of this material. A very important parameter, especially for this application today, is tan delta, or simply the ratio of loss modulus over storage modulus. This parameter is very important for us, especially for the glass transition temperature, since obtaining the glass transition temperature of polymer and viscoelastic materials using tan delta is the most accurate method that currently exists. And comparing like the classical methods of obtaining glass transition temperature, for example, will be DSC, but obtaining glass transition temperature using tan delta and a DMA test is 100 times more accurate than other methods available. So this is a typical graph of a DMA test in temperature sweep. So basically we start applying a dynamic periodic load on the sample, starting from low temperature, and then we ramp the temperature up to higher temperatures. And so for any type of viscoelastic material at lower temperatures, you have the glassy region where the material is harder and stiffer. and more resistance to deformation. By heating up the material, you will hit the transition region or the glass transition range of the sample. And so if you keep heating up the sample, you will be in the rubbery plateau region, which material becomes softer. And it's very important in terms of application and how material functions at different temperature. For example, starting from glass transition temperature, the material starts showing behavior of a rubbery material, which is very important. And that's why it is very important to understand the glass transition temperature and in what state in terms of stiffness our material exists at a defined temperature. And by heating up a sample higher, the sample will experience the viscoelastic liquid, which is the softest state of the material, viscoelastic materials. The blue line shows the storage modulus, which is the resistance of material to deformation, and it's the storage modulus is the part of complex modulus that shows the ability of the material to store energy, and the red line shows the loss modulus, which is the ability of material to dissipate energy through heat in the matrix of viscoelastic material. And as you can see, by heating up the sample, entering the glass transition region, the storage modulus will drop, and you see a peak in or increase in loss modulus since the material becomes softer. And so, as an example, this is the glass transition temperature of PMMA for standard polymer. And you can see how tan delta, which is the ratio of loss modulus to storage modulus, shows different quantity in the graph. And as you can see, so the point for us that we can determine and obtain the glass transition temperature is by running a temperature sweep on a sample using DMA. The peak in tan delta shows us the glass transition temperature of the material, and that's the method that is 100 times more accurate than any other methods to obtain TG. It is important to mention that TG shows itself with the material becoming softer. So using other methods that use, for example, energy to calculate the softness and becoming the material becoming softer is more complicated, and there's more calculation to that. But the way that DMA works is, so the material is becoming softer, and DMA mechanically deforms the sample. So it's more of a direct measurement, and the DMA is more sensitive because it's directly evaluating the softness and stiffness of the material. So the response will be recorded quicker and more accurate. And yeah, so again, a peaking tan delta shows the glass transition temperature. So here's the test results from a temperature sweep on condom materials. The blue line shows the latex-based, and the orange line shows the polyurethane-based condoms. And so again, we can see the tan delta quantity on the y-axis, and there's peaks. The peak on the left-hand side with the blue line shows the latex condom glass transition temperature, which is at -60, and for polyurethane it shows -25. So here, the application for condom using glass transition temperature can be explained in this way, that latex condom shows glass transition temperature at lower temperatures, which means at temperatures higher than glass transition temperatures, for example, room temperature or human body temperature, which is 37, around 37 degrees C, the material is softer compared to polyurethane, for example. And the material being softer means that it's more capable of taking the shape. For example, in the condom application, it's more capable of taking the shape of its application. And so it feels more realistic and different. It will be different than a material like polyurethane, which is more stiffer at room temperature or human body temperature. Uh, this is only one application within many different applications for viscoelastic materials or condoms. And so here is my part for mechanical properties of a condom, assessing the glass transition temperature.
Alrighty, thank you, Arya. So folks, getting towards the end of today's session here, going into a little bit of an outro. These webinars are something we put on quite regularly. If you have interest, we've referenced some of the past webinars done that would go into some, more specifics in some cases, a little bit more on the theory, a little more on the fundamental side rather than application focused. But on our website, there is a repository of all the webinars we've done over the past few years. Also a tech library to check out, which will include many of the application write-ups, and also different publications and collaboration pieces that have been published. So you can take a look there for any additional resources. I'll mention we do have an upcoming webinar scheduled for the end of February. This is on measuring thermal conductivity on a budget using the thermal conductivity kit. So again, today's content was all generated using the Trident platform, which is certainly more of a research grade level instrument, a lot more capabilities. But the TC kit offers a nice entry level point to getting just some initial basic thermal conductivity testing. It uses a TPS. There are some specific differences between the two platforms, and if you want to learn more about that, please feel free to join us here coming up in I think that's what, 2 weeks? Yeah, 2 weeks from now. I'll also mention some of the in-person events we will be at. February 25th to 28th of this month, the thermal management for EVs and HEVs. This is being held in Munich, Germany. If you happen to be in Germany at the time, or you're from Germany and you're planning to attend, please feel free to come and check us out. I'm not sure if we have a booth there yet, but I'll double check that, and if we do, we'll certainly be updated. Early March, so I guess right after the thermal management in Germany, we'll have some folks at PitCon, which is being held in Boston, in the US. Again, that will be March 1st to 5th. And then the one, I guess, kind of overlapping, some other colleagues of mine will be at the JEC World 2025. This one is being held in Paris, France, March 4th to 6th. So if any of the content here was of interest, maybe it, directly related to what you're working on, or maybe I'll call it, tangentially related, we're certainly happy to take it a little bit of a step further, go a little bit more of call it a tailored presentation, more of a deep dive on what you're looking to do with thermal conductivity or thermal analysis or mechanical analysis. Please feel free to reach out. We'd be happy to schedule a technical consultation where we could go into these applications or methods in further detail. Also, maybe if you kind of have an idea of what you're looking for already and you just kind of want to get some budgetary information, either for instrument purchase or for contract testing needs, please feel free to reach out. We're, again, happy to provide a quote, give you some budgetary information on what that would look like. Lastly, I'll plug our LinkedIn. This is where we post all of our latest and greatest content, any upcoming events, webinars, everything that we're doing will be on LinkedIn first. If you're not doing it already, give us a follow on there, and that's how you'll really be able to keep up to date with what we're doing. And at this point, this brings us to the end of the formal session here today. We're going to go into the Q&A at this point. So this will end the official recording as well. So if folks have to drop off, thank you very much for joining us here today, and I hope to see you at the next one. For folks that are sticking around here, give us a minute and we will jump into a Q&A.